Hello, folks. Ooh. Well, I have bad news for you. I just lost my entire work. Oh, well. Whoa. That's not what I want. Okay. Let me continue where we left off last time. We were talking about joint PDFs, and I had put up a problem called Buffon's needle problem. And the problem was as follows. You have this infinite plane that is ruled by lines a distance d apart. Okay? And you have, where does that come from? And you have a needle of length L. So the needle length is needle length is L, and it's less than or equal to D. And you drop this needle randomly on the plane. And you want to figure out what's the probability that this needle will cross a line. Okay? Now the equality sign here shouldn't bother you because the probability of the needle landing exactly vertically and each of its tips hitting adjacent lines is 0. And we don't worry about events of probability 0. If it really bothers you, you can make that length strictly less than d. It won't matter. So, let me erase this one line. I don't need that. So here's the question. So what's the probability that the line, or that the needle crosses a line? Okay? So to set up the problem, I'm going to take the midpoint of the needle and I'm going to label its distance from the nearest line as x. So x is distance of midpoint of the needle to nearest line. Okay? And I'm going to take as the other variable, we're living in a two-dimensional plane, so I need two coordinates for this thing. I'm going to take capital theta as the angle that it makes with the horizontal. Are we all good? Yeah. What is what? Oh, sorry. I had labeled it in my previous document and my computer decided to reboot all of a sudden and I apparently forgot to save. D is the distance between these lines. Okay? All right. So, can you tell me how I would label this diagram if I were to articulate what it means for the needle to cross a line? What does it mean for this needle to cross the line? I want everybody to think of it. Talk to your neighbors and see what that would mean. me see if I can rapidly remove this tablet from the keyboard. No, it's not letting me. Okay. Rohan. Louder, Rohan. I still can't hear you. Hold on. You got a problem.
We know that we know that like one half of the needle will have length L over 2 because the whole needle has length L. So I drop perpendicular from the end of the needle.
End of the needle down to
a line that's parallel with the midpoint of the needle
and crosses the midpoint. So this is the midpoint right here. Midpoint. And we draw a vertical. And how would you describe the event that the needle crosses the line?
It's equivalent to the inequality, saying that sine of theta times L over 2 is
so hold on. So this thing here is L over 2. We've got a right triangle. Its hypotenuse is L over 2. What's the length of this blue drop line?
The length of that will be sine of theta times the hypotenuse, which is sine of theta times L over 2.
So that's L over 2 sine theta. Okay. And the event that the line crosses is what?
So, L over 2 times sine of theta is greater than or equal to x.
So this probability is the same as the probability that x, meaning the distance from the midpoint to the line, is less than or equal to L over 2 sine theta. Okay? Is everybody here? Yeah. So the needle will cross the line if the distance from its midpoint to the nearest line is less than this side of the triangle. Right? If it's equal to that side of the triangle, that means the tip of the needle is just touching the line. Right? Okay. So this is the event we need to find the probability of. Now, what I'd like you to do is tell me what the probability density is for the two random variables in question. I've got the random variable x. What's the probability density function for x? And what's the probability density function for theta? So I have got small theta here, f capital theta, small theta. Remember, I'm throwing the needle randomly. So what do you expect the density for x to be?
Would it be a uniform distribution?
Okay, it's uniform from where to where?
0 till...
You have the microphone. You got the microphone.
0 till... Oh, wow. 0
What's
till
your name?
Saurav.
Saurav?
Yeah.
Go for it.
0 till whatever the... Yeah, what is it?
What is the whatever? We said x is the distance to the nearest line.
D over 2.
Nearest line.
D over 2.
2? What the heck? Let's throw numbers.
Well, D over 2 because...
So x must be above the midpoint between the lines, right? It's from the midpoint D over 2 to
D.
0.
Oh, 0, sure.
So what do I label this?
D over 2.
D over 2. And then this would be? What's the height?
1 over D over 2. Is that right?
1 over D over 2, which is?
I don't know,
2 over D. I gotta have unit area, no?
Yes.
It's a density.
Indeed.
This is all part of the modeling process. I'm taking you through a modeling process. So, and what about the angle? That also should be uniform, right? There's no reason why the needle should favor a particular angle over another angle.
Indeed.
So what's a good angle here?
I would say 90 because I guess the other
Pi over 2, yeah. And then this would be?
2 over pi.
2 over pi. That makes the area of that rectangle equal to 1. And there's no reason why the distance and the angle should be in any way dependent on each other. So we're going to assume that x and theta are independent. Okay? So if you were to plot the joint PDF of these two, what would it look like? If I were to plot the theta here and the x here, what would that look like? Talk to each other. This here. Okay. So if you get to pick the next person.
Kevin.
Oh, we gotta do a random sampling around the room. Okay, Kevin can do it right now. But then I want somebody else from across the room.
Young man in the gray sweatshirt on his phone.
What was the question again?
How would I the first question is, what's your name?
Vlad.
Vlad.
Yeah.
What's the joint density of x and theta if they are independent?
Well, I think we can plot theta on theta. So it's going to go from 0 to pi over 2.
Pi over 2.
X is going to go from 0 to d over 2.
D over 2. And so this is the footprint of the PDF. Remember, we're talking about a joint PDF of two random variables. So the PDF is actually sitting on top of this plane. And when we talk about probabilities, we're talking about probabilities as volumes under that surface. But what's the shape of the surface?
The shape of the surface, maybe it's going to be like a cap kind of thing.
Aren't these uniform?
They are uniform.
So and they're independent. So can't I write this?
Yes.
So if you multiply two uniforms, what do you get?
I don't know.
Well, it's this height times this height.
Right. I mean, yeah, it's just.
So I have this rectangular, three-dimensional rectangular cube that has a height of 4 over pi d. It's this peak times this peak.
Mm-hmm.
Okay. Now, I'm interested in the event probability of x less than or equal to L over 2 sine theta. So I want you all now to think about how you would write that. Theta can go from 0 to pi over 2. Okay? I'm going to write this integral in a weird way. So theta goes from 0 to pi over 2. what should I put as the limits for x? And remember, this is the density, the joint density. I have to integrate the joint density over an appropriate region in the two-dimensional plane. So what should I put as the limits for x? Talk to each other, people. Okay. What do I have for the limits? I'll take a volunteer. X goes from what to what? Go ahead. What's your name? Yeah. Adrian. Go for it, Adrian. L over 2 sine theta. And our density is nice. It's constant. So I can just pull it, and then its value is this. So I can just pull that out. So I've got 4 over pi d, integral from 0 to pi over 2. And when I integrate this is gone. So I integrate from 0 to L over 2 sine theta. So I have an L over 2 sine theta d theta. Can you guys do the integration and tell me what expression you get? Obviously the L and the 2 come out. So the 2 cancels with that. I get a 2. I have an L here, and I've got a pi d, and I'm integrating the sine from 0 to pi over 2. That's all I'm doing. What's the answer? Shout it out. Yeah. Yeah. Sorry, I can't hear. The height of this density is 2 over pi. So that's what this factor is. The height of this density is 2 over d. Do you remember why we put those values as the heights? What was the reason? Exactly. So now I have to multiply the heights of these two densities to get the joint density at any point small x, small theta. So what's the value of the density for theta at any small theta of interest where the joint density is non-zero? It's 2 over pi. It's like multiplying two constant signals. So I'm multiplying 2 over pi by 2 over d. That's 4 over pi d. So that's the value of my joint density where the joint density is non-zero. Okay. So what's the final value? Boy, we've got a lot to cover. Come on. This is from last lecture leakage. 2L over pi d. Okay. This is great. Because if you're one of those folks like this dude, Lazzarini in 1901, who was so rich and had so much free time on his hand, that he actually built a machine that tossed needles on a surface and his machine actually tossed the needle on a ruled surface 3,408 times this guy's machine threw a needle on a ruled plane. And of those, he noted that 1,808 cases, this is Lazzarini, 1901. And he noticed that 1,808 cases crossed the line. Can you tell me how to estimate pi from that? D equals L? No. L is known, D is known. You've figured out what this probability is. Have you? That was the whole point of his experiment. He wants to estimate that probability. What's one of the interpretations of probability? Counting. Frequency interpretation. You run an experiment a large number of times and see out of those times how many times a particular event happens. It's a Bernoulli trial. Each time you drop the needle, it's a Bernoulli trial. Either it crosses a line or it doesn't. So out of 3,408 times, he measured 1,808 times when the needle crossed. So what's the estimate for the probability? This divided by 3,408. In other words, the number of crosses over the total number of trials. Actually, I should use small letters for these because I promised you I'd use large letters for. This is N, and this is M. N total number of trials, M total number of successes. So I've got M over N is equal to 2L over pi D. And M over N is an approximation to this probability. That's the whole idea of the frequency interpretation of probability. Okay? So pi is equal to what? Pi is approximately equal to, read it out, people, 2L N over MD. And he actually measured it to be this. Not bad, eh? I bet you Mr. Jones in your trigonometry class never talked about Buffon's needle and how to calculate pi. They just made you measure the circumference of a circle. Okay, so I like this problem because it pulls in a whole bunch of concepts, and at the end there's a surprising result, which is actually you can estimate pi using experiments, the experiment of dropping a needle. Any questions on this? Yeah. Oh, were you stretching or you quit? Okay. Is it the case that the more experiments you do, the more accurate pi will be? Well, that's a great segue to today's lecture, which is about the law of large numbers and the central limit theorem, and how by running an experiment more and more and by averaging you can actually get better and better estimates of things. That's exactly right. That's very good intuition. So I'm going to give you a 1.5 minute break, and then we will move on to the sequence of topics that lead ultimately to the central limit theorem, which is one of the major results in probability theory. Okay, so take a 1.5 minute break. I know the break is coming early today, but we're at a good juncture. And in the meantime, I'll try to detach my tablet from the rest of the computer.
So can I just ask a question about
All right, that's good. One moment. There we go. Yes.
So I think the theta should be like 0 to pi, no.
Okay. Let me give you the roadmap for the rest of the session. It's likely, given how long this example took, that will leak into Thursday. So I'm going to talk about a few intermediate results before we get to the central limit theorem, which builds on them. But I'll tell you who done it, so that you don't have to live in suspense about what's coming at the end. So I'll take you straight to the end of the book and tell you what the central limit theorem essentially says. Suppose you run an experiment, a large number of trials, and you add some random variable associated with each trial, and they're all independent, identically distributed. It turns out independence is not required, nor is identical distribution. But we'll consider the special case where the trials are independent and identically distributed. And you add up all these random variables together. It turns out that the distribution of that sum approaches that of a Gaussian random variable as the number of trials increases. So, for example, if you're running a Bernoulli trial n number of times, and the example that I will develop for you is a pollster problem. So suppose you want to figure out the true fraction of the population in the United States that believes, say, marijuana should be legalized. Okay? You want to figure out what that fraction is. You want to determine how many people you've got to go out and poll to get a good estimate of that fraction. Polling is essentially one of the areas where this comes into play. If you notice, every time the political season comes or whenever they run a poll, there's always a plus-minus error they give you. They say, okay, this percentage of people believe in this. The margin of error is plus minus 3% or what have you. So that's essentially what we're going to develop. And the nice thing that allows us to figure out the number of people to poll to get that result is the central limit theorem. And everything boils down to figuring out probabilities on the Gaussian curve. So that's the end point that we're trying to get to. But there are some intermediate results that we're going to have to go through. And I'm going to give you the trajectory for those. First, I'm going to develop a tail probability formula. Probability formula for non-negative random variables. This has a discrete version, discrete RV version, and an analogous continuous version. Okay? From there, we're going to move to this thing called the Markov inequality. From there, we're going to move to another inequality called Chebyshev. I'm giving you the roadmap so that when you go and review your notes, you don't get lost in what we're doing. And I'll come back to this trajectory as we go forward. And then from here, we go to the law of large numbers. And from there, we go to the central limit theorem. So we've got to go through a whole bunch of stops to get to where we want. And even then, we end up talking about what is referred to as the weak law of large numbers and a very special form of the central limit theorem, not the most complicated form that mathematicians and statisticians worry about. Okay, so that's our trajectory. 1, then Markov, then Chebyshev, and then weak law of large numbers, and the central limit theorem. So what does the tail probability formula say? So let's look at the tail probability formula. Each one of these, by the way, is pretty cool in its own right. Tail probability formula. I'm going to develop the discrete version for you and then give you the continuous version and then work off of the continuous version. I'd rather deal with sums than integrals when I can. Okay, so what does the tail probability formula say? Suppose x is a non-negative discrete random variable that takes on these values. So non-negative random variable. Okay? The tail probability formula says that the mean of x can be written as the summation from 0 to infinity times the probability that x is greater than k. And of course, you recognize that as what? What is this probability? By definition, what is that? Complementary CDF. Oops. Complementary CDF. This is totally unintuitive. If you don't know why that equality holds, don't worry. But that's the formula. Why do we call it tail probability? Because each of these terms involves a tail probability. The probability that the random variable takes on values to the right of some threshold. Okay. Well, I don't know about any of these fancy schmancy equalities. I just know my basic formula. What is my basic formula? That the expected value of x is what? The sum? What? K times? Probability x equals k. That's my definition. But you have to tell me what the limits are. In the most general form, the limits are from minus infinity to infinity. But not here. 0 to infinity. Why? Because I restricted x to be from 0 to infinity. I started by saying x is a non-negative integer valued random variable. So my summation goes from 0 to infinity. Okay, well, let's write this out. The zeroth term, k equals 0 term, is 0 times p x 0. The next term is 1 times p x 1. The next term is 2 times p x 2. You know, if my 4-year-old was here, she would go, let's do Baba, p x 3. And you know what they say about small children, especially toddlers. Hey, that was fun. Let's do it 200 more times. Let's go 200 more terms. I'm going to rewrite this sum in the form of a pyramid. So this term is 0. Let's knock it out right now. This term here, I'm just going to write as px1 times 1. Actually, I don't need that. Plus, I've got two of these guys. So I'm going to write one of them here, and then one of them down below. Are you with me? How many of the other one do I have? 3. So I'm going to write one here, and one below. And I'm going to keep doing this. Okay? So I'm summing all these rows from here down. So the fifth one here, I'll have 5 terms corresponding to it. Is everybody good? All right. Now tell me what the first row means to you. Let's turn this into a humanities social science class. What does that sum mean to you? Does it speak to you? Does it call on you? What does it whisper into your ears? This first row. Everybody. Fx of what? Fx of 0. The second row is fx of, right? Look at this row here. Oh, I'm sorry, fx of 1. I'm adding up all the probabilities of x taking on the value 1, 2, 3, 4. Well, that's the complementary distribution function at 1. The second one is fx at 2, 3. Well, that's the result I wanted. This is simply the sum of k equals 1 to infinity fx complement k. Well, this is 0. No, wait a minute. What am I missing here? There's something. Yeah, let me write it in terms of probabilities before we get all confused. So let me write this as first row is the probability that x is greater than 0 plus the probability that x is greater than 1 plus, so I have the probability, I have the sum from 0 to infinity that x is greater than k. And what is that by definition? This guy here? You've already told me. That. We're done. So that's the tail probability. So it's a way of expressing the mean of non-negative random variables. Can you tell me what the continuous version would be? So if I have a random variable x that is always that is non-negative, e of x can be written as what? Instead of the sum, I have what? Louder. Integral. From where to where? 0 to infinity. Of what? Fx complement of x dx. This is the continuous version. Okay? So we're done with item 1. Why do I need this? Let's look at our roadmap again. I want to jump to this equality called Markov equality. Which says that So let's go to station 2 now. I hope you got your tickets. Markov inequality, sorry. Markov inequality. Markov inequality says if x is a non-negative random variable, the probability that x is greater than or equal to some value a is less than or equal to the expected value of x over a. So loosely speaking, if a random variable has a small mean, the probability that that random variable is very large is, if the mean of the random variable is small, the probability that x is very large, in other words, if I put a large value a here, that probability is what? Small. So if the mean of a random variable, if e of x is small, this is a qualitative interpretation, then the probability that x is large is low. Okay. Now, how do I show this? Okay, let's go back to the, what is this doing here? Come down. I'm going to go back to this guy here. And I'm going to draw things out. Can you talk to your neighbors and figure out how you would draw the complementary CDF for some typical reasonably behaved random variable that is non-negative? Remember, we're talking about non-negative random variables here. Complementary CDF. At 0, it's what? 1, because all the probability is sitting to the right of 0. So you know that the curve starts at 1. Okay? So if x is greater than or equal to 0, then the complementary CDF at 0 is 1. Because all the probability, there's no probability sitting on the negative side. All the probability is sitting on the right side. And as I go toward infinity, what happens? So as I increase the value of the threshold, the probability sitting to the right approaches, everybody, 0. Okay. And the CDF, we said, was non-decreasing. So as I go to the right, the cumulative distribution function starts from 0 and increases to 1. So what do you think the complementary CDF will do? It's non-increasing. Very good. So it's going to have a shape like that and approach 0 as I go to infinity. Now, what does this probability mean? If I pick an alpha here, let's pick, red. Not alpha, A. Then this value is what? This value right here. Fx complement at A. But what does that mean? That's the probability of what? X is greater than A. For a continuous random variable, unless there's some kind of an impulse sitting there and it takes on the value A with non-zero probability, putting an equality sign here won't matter. What is this area here? Can you tell me? A times Fx complement A, which is A times the probability. Everybody, come on, let's sing along. X greater than or equal to A. I'm tone deaf, I'm sorry. Okay, so that area is A times the probability is greater than or equal to A. Right? That's the probability of that rectangle. How do you compare that to the total area under the complementary CDF? If I were to shade all of this, how does that red area compare to the purple area? Would you say it's greater than, equal to, less than or equal to? Less than or equal to the purple area. Whoa, not that. That. But what is that purple area? Isn't that just the integral from 0 to infinity of the complementary CDF? Yes or no? Yes. Very good. Well, we have our inequality then. I just take this A and put it on the right-hand side. Oh, and what did we say about that area? No, it's not equal to 1. We go back to station 1. It's the expected value. Yay! Here we go. Nice. I'm proud of myself. So now we have A times the probability that X is greater than or equal to A is less than or equal to the expected value of X, which brings us to Markov's inequality. I don't know why the guy got so famous. I just derived it. This Markov guy is all over probability and statistics. There we go. That's Markov's inequality. Yep. Pardon me? Complement here. Yes, correct. Thank you. Okay. We have reached station 2, people. Now the train's about to take off to go to station 3, which was what? Chebyshev's inequality. You get a sense all these folks from Eastern Europe had serious contribution to math. I have math envy. Chebyshev's inequality. Okay. Chebyshev's inequality falls right out of the belly of Markov's inequality. It has an independent derivation as well, but since we have developed Markov's inequality, we can just grab Chebyshev's inequality as a special case of the Markov inequality. So suppose I have a random variable x that's non-negative, and I know that this is true about x. Okay? Now I'm going to define a random variable y. So there's nothing sacred about x. X can be anything, any non-negative random variable. I'm going to define random variable y as x minus its mean quantity squared. In other words, y measures the deviation of x from its mean, but squared. Okay, so not the absolute deviation from the mean, squared deviation from the mean. Do you agree that y is a random variable? Yes, of course it is, because it's a function of the random variable x. Do you agree that y is non-negative? Yes. So, what does Markov's inequality tell you about y being greater than or equal to a? It's what? Less than or equal to the expected value of, everybody, y over a. But what is the expected value of y? It was the expected value of something squared, no? X minus e of x squared over a. Are we all here? Excellent. Now I'm going to write this by massaging the left-hand side of the inequality so that we have everything in terms of x. So the inequality I have says that the probability that x is away from its mean by more than a certain amount is less than or equal to the expected value of x minus e of x quantity squared over a. But what do you recognize the right-hand side's numerator as? The variance of x over a. And here we have it. This is Chebyshev's inequality. In fact, I can just put absolute value here. The probability that a random variable is away from its mean by more than a certain amount is bounded by a linear multiple of its variance. This is Chebyshev's inequality. And we have arrived at station 3. Do you need a 1-minute break? Take a 1-minute break. Okay. So we've covered these 3 items. We talked about the tail probability formula, which gave us an alternative way of thinking about the mean of a non-negative random variable. We used that, its continuous version at least, to prove Markov's inequality. And as a special case of Markov's inequality, we showed Chebyshev's inequality. And that's where we're going to build on, that's what we're going to build on to get to the weak law of large numbers. So, let's label this now as station 4, weak law of large numbers. Okay. Suppose I have n random variables that are independent, and identically distributed. They're IID. They all have the same mean mu, and they all have the same variance, sigma squared. Okay? In the case of a pole, you can think of each of these xi's as a Bernoulli random variable. I go to the ith person and I say, do you believe, in your opinion, should marijuana be legalized? He or she will say yes or no. If they say yes, I mark a 1. If they say no, I mark a 0. Okay? And then the fraction of the population that believes marijuana should be legalized would be mu. The problem is I don't know what mu is. Unless I go and poll every single person in the United States, I won't know the exact value of mu. And I don't want to know the exact value of mu. I just want to have a reasonable estimate of mu. Okay? I can define the sum of these random variables as this. Oh, please. Oh, no. What are you doing? Go away. How do I get out of here? How do I get out of here? Boy, you just got yourself another break. That is not what... Let's see. Go away. Escape. Do you want to exit tablet mode? Yes. Oh, there's an X. What did I just do? Always look for an X. Ready to detach. Yes. Excellent. Okay. So, I define the sum of these variables as Sn, and I define Mn as the average of these. This is called a sample mean. Okay? So, you run an experiment a certain number of times, you want to figure out some average value, you add up all the random variables, divide by the number of trials. That gives you a sample mean. So, with regard to the earlier question, as n increases, you would like the sample mean to approach what? The true mean, in some sense. You want to have a better and better, you want this Mn to be a more accurate version of the true mean as you increase the number of people you ask, or as you increase the number of random variables that you average over. Okay, well, is that the case? Here's what I want you all to do. So do you agree that Mn is a random variable? Yeah, it's an average of a bunch of random variables, so it must be a random variable. What is the mean of Mn in terms of the means of the individual random variables? Let's see how good an instructor you had who at some point talked about some property or other of expectation. How would you figure this out? N is fixed. You've picked the number of trials. N is a small letter n. It's not a random variable. So how would you do it? So this is the expected value of all these terms divided by n. What do I do with the n? Take it out. And then the expected value of the sum is what? Sum of the expected values. This is from 1 to n, but they all have the same mean. So how many mu's am I adding? N mu's I'm adding, and I'm dividing by n. So notice the expected value of Mn is mu. Sample mean should approach the true mean in some sense that I haven't yet defined. The true mean is if you knew the exact probability law governing the xi's. Yeah. So in the case of the poll, if you knew the exact fraction of the population, there are two ways you can figure out the true mean, right? Either you know the exact probability law. In any polling situation, you obviously don't know that. Or you go and look at every single sample point, meaning every single person in the United States who is a voting person who votes, and find out if they believe marijuana should be legalized. Okay? Then that gives you the true fraction, the true mean. Okay? So here we have this nice situation. Mn is called an estimator for the true mean. We are using the sample mean as a way to estimate the true mean. And one of the nice properties of a good estimator is that it be unbiased, meaning that when you take the expected value of that estimator, you get the true mean. So Mn, we say, is unbiased. That's a side point. It's not something we're going to harp on in this class, is an unbiased estimator of mu. So that all that says is that when you take the expected value of Mn, the estimator in this case Mn, you get the true mean. And what's the variance of Mn? Can you work that out with your neighbors? Why do I need the variance? What do I want to show with the variance? You should also be asking that in the back of your minds. What does Chebyshev's inequality have on the right-hand side? It's got the variance. Adrian, you get to pick the next person. No. We want the flame under everybody's feet. Is it on? Turn on the switch. Give it a moment. Yep.
Hello? Hello?
Yeah, you are.
Borhan?
Borhan!
How's it going?
Not bad. Go for it, my man.
Initially, I was just thinking we would use...
Keep it closer to your mouth. I can't hear you still.
the formula we've always been using.
Okay, so what happens to the 1 over n?
Well, it doesn't...
So remember, this is the variance of Sn over n, right?
Yeah, and...
The random part is in the numerator.
And n is a constant, so it doesn't affect the variance.
So it does affect the variance, but how? when we scale a random variable by some scalar quantity, in this case 1 over n, what happens to the variance of the new random variable? What happens to the 1 over n?
It's squared. Isn't it squared?
Squared. So 1 over n squared comes out, and then I have the variance of Sn. And that's the variance of the sum. So variance of x1 plus x2 plus xn. And what do we know about the random variables x1 through xn? Is your name Borhan?
That they're identical, or like identically distributed.
They are what?
Identically distributed.
Identically distributed and?
Independent.
Independent. So how does independence help you? Variance of the sum becomes?
Sum of the variances?
Sum of the variances. You turned it off.
No,
or
I
the
didn't.
battery. So it becomes the sum of the variances. And they're all identically distributed. So I've got sigma squared plus sigma squared plus sigma squared. Right? N terms. And I've got a 1 over n terms. So I've got n sigma squared over n squared. That gives me sigma squared over n. That's the variance of the sample mean. Are we all here? Excellent. Notice how we're using all these properties that we've been talking about for the expected value. The linearity of the expected value. Variance of a sum is not in general sum of the variances, but because they're independent, we can write that as a sum of the variances. Question? Ooh, very good question. So let's do a detour here. The question was this: why is it that I cannot write variance of x1 through xn? I'm claiming this is n times the variance of xi, because they're identically distributed, and because so I'm claiming this is the case. This is the variance of the first guy, second one, all the way to nth random variable. So it's n sigma squared. That's what I'm claiming. Your question is, why can't I say variance of x1 to xn is variance of n times x I, and write that as n squared sigma squared? Can somebody answer that question? That's a very good question. Why is it that I can't say that? This is incorrect. This is incorrect. Yeah. They're not all the number. You had it all right until that number 1. They're not all the same. They're not identical. You are taking the variance of n times a single random variable. But these xi's are different random variables. They follow the same probability law and they're independent, but they are different. They correspond to different trials of our overall experiment. N times x is a single experiment where you go and ask one person, do you believe? If I just measure x, it's akin to asking only one person, what do you believe? And then extrapolating by multiplying that by n. That's not what we're doing. Okay? Very good point. Okay. So what do we have here? We've got the mean of Mn as this, and we've got the variance of Mn as this. Can you tell me what Chebyshev's inequality says? Now that you have these two, Chebyshev says what? The probability that, help me out here, people. What's my random variable of interest? Isn't it the sample mean? Minus the expected value of the sample mean. Chebyshev says the probability that that is greater than or equal to some number A. Hold on. That's actually important. This is A. What happened? No, hold on. There's a square term that I missed. A squared. I should have put a square here. So I'm going to put a square there and a square here. And then you can derive it from the Markov. I think that's where I made the mistake. Let me see. A squared is the same as, so here's where I goofed. I am interested in x being away from its mean in the squared sense by more than this, but this is the same as the probability that x is away from its mean in absolute terms. Do you agree that these two probabilities are equal? Are they equal? To say that something squared is greater than some threshold squared, isn't that the same as saying the square root of this left-hand side is greater than or equal to the square root of the right-hand side? Huh? Now, what does Markov say? That this is equal to what? Isn't that what it says? If I apply Markov, so this is actually, I should have put a square here, so that I would have a square here and a square here. That's where I messed up. See, I wanted y to be greater than, because y is a square quantity, I want the threshold on the right to also be expressed as a square quantity. So this number, whatever it is, it shows up in the denominator here, and it shows up in the denominator here. So now, this is square, and this is square. So that's what it says, and this is finally what we have. Okay, now we're good. All right, so let's go here. What does that say now? The numerator is the variance of Mn over what? Over what? No, A squared. Here. Okay, but what is the variance of Mn? What did we say it is? It's what? Sigma squared over n, no? Isn't that the variance of Mn? It's right here. What happens when I take the limit as n goes to infinity? Can you tell me? What's on the right-hand side? When you take the limit of the right-hand side as n goes to infinity, what do you get? 0. Now make this a as small as you like. Make it an epsilon, smaller than epsilon, whatever Greek letter you believe in is the smallest thing possible on the planet. What this says is that as you increase the number of terms, the probability that your sample mean is away from the true mean. Remember, this is the true mean. Didn't we show this? We showed that Mn is an unbiased estimator. The expected value of Mn is mu. So this is saying that the probability that my sample mean is away from the true mean by more than any arbitrary amount approaches 0 as n goes to infinity. In other words, I am getting progressively better and better estimates of my true mean as I increase the number of people in my poll. This is essentially the weak law of large numbers. The interpretation is more important than anything else. We found, using Chebyshev's inequality, an expression on the right-hand side that is inversely proportional to n, which means that as I increase n, sigma squared is fixed, a squared is fixed. The only thing that's changing is the number of people that I'm polling. I can increase the number of people I poll. As that n goes to infinity, the right-hand side, which is the upper bound for this probability, approaches 0. So this probability is sandwiched on one side by 0, because it's got to be non-negative, and on the other side by something that is getting progressively smaller and smaller. And so this probability approaches 0. This is the statement of the weak law of large numbers. We'll deal with the CLT and the pollster problem on Thursday. Okay. See ya.